I know it's a lot, but I traveled a long way, so here we are. Uh, so before we did water, and I know that's pretty heavy duty, but what I'm about to talk about is going to be way more close to home for people who have ever stepped up to an espresso machine. This is going to be something that's probably going to have immediate impact in your cafe. So it's the project I've been working on for 4 years, and none of you will have ever heard about it. So it's my first time talking to you about it, and it's big. Okay, so before we start, I want to show you a couple of things. Espresso machines are becoming more prevalent in the scientific literature. A publication in Organic Letters, a legitimate American Chemical Society journal, demonstrated that if you ground up star anise, you could gain access to shikimic acid. This compound is a precursor to anti-cancer drugs. And the way they extracted it was they ground it up and pulled it through an espresso machine. Now, in my coffee lab, we will not do this, okay? But nonetheless, it proves the point that people are becoming more interested, certainly in using coffee technology. Also, I've been traveling a little bit, in fact, more for coffee stuff in the academic realm than I've been doing my normal energy storage work. And this is interesting because it means the scientists are starting to pay attention to this being quite important. I don't need to convince any of you that the industry is important. Of course, it's worth a tremendous amount of money in the United States. So much so that actually NASA has invested $1.6 million in developing a cup that you can drink liquids from in space. The idea is simple, that you put it in a cup and the surface tension of the liquid wets the cup and it allows the liquid to flow towards your mouth and then you drink it out of this cup. Astronauts you need to spend $1.6 million so that an astronaut can drink some coffee in space. It seems reasonable. I'm about to show you a picture so I've seen this cup, but this is like a replica. It's questionable looking. So this cup is at the University of Pittsburgh Quantum Institute. They contributed to its design. The way it works is you put your mouth here, and because the liquid it wets this channel along there, it'll pool up right there, and all you do is you just suck right here, and then you're good. So, and there's videos online if you'd like to look at it. So what we're going to get to now is what that liquid is that inevitably ends up in that cup, and this is we're talking espresso now. Okay, we're getting straight into it. You got all these grinders. The key thing about a grinder is that the biggest particle that you want in your grind is the particle that can just make it through the aperture of the burrs. And so these particles get fractured and eventually they will exit the grind chamber. And in these two technologies, they do. I mean, everybody here is familiar with a conical burr set and a flat burr set. The reason the blade grinder is no good is because once the particle is sufficiently small, it remains in the grind chamber, so it can get further fractured, which just results in a spread in particle sizes, and that's just a problem, right? It's not being fancy, and this is how I like to tell people who say, what grinder should I buy? It's like, just get something that lets the particles out when they're small. So we have to quantify how small they are, and so the way you do this is you shine light on particles as they fly through space so that they're all separated and you can quantify their size. But the problem is that we have to approximate them as a sphere because we really are just getting an instantaneous measurement of a diameter. And so the sphere is the best we can do. But if we use a scanning electron microscope, you can see that for a particle of ground coffee, that in fact, this is quite a large particle, so 100 micron here. So this particle is, let's say 1,000 micron across. This is a big piece of coffee. There's holes in it, and these holes are where the cell walls of the coffee used to be before you roasted it. Then you roast it, there's no more cell walls, so you've got all these voids. But what's interesting is actually this stuff, the stuff on the outside. If you zoom in, these are actually very small particles. Note the 10 microns. These are little things. Now, this looks like a bit like a conch shell, for example, but we can't tell what orientation it is when it flies past the detector, so we call it a sphere. I know it's not great. That's the best we can do. We're asking a question like this. This is a sea urchin, and is the sea urchin this big, or this big? Okay. Obviously, the answer is it's this big, right? But again, we're measuring this. And it turns out, actually, as you get to smaller and smaller particles, a sphere becomes a better approximation. And this just happens to be, it's just a coincidence for coffee that as you grind small, they become more spherical, okay? So the spherical approximation holds true as long as the coffee is pretty small. But we always get the question about coffee being porous. So I did the measurement to show that coffee is, at least on the atomic scale, is not porous. It's quite dense. And so the way you do this is you add nitrogen gas, and this is at the temperature of liquid nitrogen. So at low pressures of nitrogen gas at the temperature of liquid nitrogen, it's still a gas. And eventually you get to the pressure of 1, and at this pressure, nitrogen gas condenses to liquid nitrogen. And so if there's little tiny holes or channels inside something, then you're going to have liquid nitrogen show up in those channels, okay? And so all we do is quantify a change in pressure based on a known amount of nitrogen we dose in. A system that is really porous would have a value of a volumetric uptake of nitrogen on the order of thousands. Coffee is on the order of 5 or something, 7. And so this is really low. This is what you'd expect if you had a surface, a material with a surface and nitrogen was just depositing on the surface. So from this we say, okay, maybe those macroscopic holes, they're there, we can see those, but they're not gonna contribute to mass transport limitations in an espresso puck. That's good. So treating coffee as a hard sphere seems to be a good thing to do. So if we then turn to the particle size distribution, this shouldn't say submitted, you'll see the reference coming up. This paper was published in 2016. That we note that as we grind on an EK43 at grind setting at 2.5, you get a characteristic particle size distribution where you have this large peak here, and this is, note, the volume percent, and then you see a smaller peak here. Now, a volume percent is a measurement of, if you took 1 milliliter, 1 unit of volume, how much of that as a percentage is occupied by those pieces. So it shouldn't surprise you then that big pieces occupy a lot of volume. Little pieces occupy a little bit of volume. So if you normalize then by just saying how much surface area comes from these particles, the picture looks a little different. The big pieces now only contribute between 15 and 25%, and even though these little pieces don't take up much space, they give about 75% of the surface area in that puck. But then, if you were to count, like I taught you before as a chemist, where you just count how many there are, it turns out that there are 100 million little pieces for every one big piece. Okay, so the puck is made of fines. That's the first thing that you take home from this slide. Second thing is that as I grind finer, the big pieces get smaller. That makes sense, right? Because the aperture is closing, so the biggest particle that can make it through the aperture is getting reduced. But the population of fines is increasing, but not getting finer. In other words, we have big pieces getting smaller and fines increasing in quantity. And the reason for this is that fines are produced at the fracture interface when you break this big piece into smaller pieces. So every fracture I make dust. If I have to make more fractures, I make more dust. But the dust is always the same size, right? Or more or less, you see, whatever. Okay, so this has implications because if a big bean enters a grinder, you're gonna have to fracture it more times than a little bean, which means a big bean is gonna result in more fines produced at a given grind setting than a little bean. So that's problematic. So if you have Marigo, no, what is it? No, not that one, the one you have. Maracatu, that big thing. If you put that in your grinder, and assuming it's of the same density as a little coffee bean, you're going to end up with different particle size distribution for the same grind setting. So that's problematic, number one. Okay, so it turns out that coffee fractures in more or less the same fracturing pattern as volcanic rock. So when a volcano shoots a rock up into the sky, the friction from the air causes the rock to fracture in different ways, and that rock starts out big and ends up smaller, and it makes dust as it flies through the air. So that's pretty neat. But it turns out that the only way you can control the size of the fines is with temperature. And so by cooling coffee, you start out initially at room temperature here, and as you cool it down to freezer, and then down to dry ice, and then eventually to liquid nitrogen, you can see, okay, maybe the size of the center of this peak is shifting slightly smaller, on the order of, I don't know, between like, let's say, 20 down to 19 to 18 microns, something like this, perhaps. But what's more important is you can see this hip here, right there, on the black line, sort of disappears. This becomes more of a smoother Gaussian distribution. Now it's a skewed Gaussian because it's not symmetrical, but it's more of a Gaussian distribution. This is a good thing from a particle science perspective. It turns out that actually we can describe exactly why this happens. So if imagine you're the solid piece of coffee. All of you are contributing to the coffee, and I'm a crack, and a crack needs to propagate through somehow. So at high temperature, all of these rows are going to be swaying left and right ever so slightly, which means if I want to go between you and then get between you, it's going to take me quite some time to go between these two cracks because you're swaying back and forth. But as I cool, the swaying slows down and the crack propagates linearly, and therefore you end up with shorter distances the crack has to propagate, making smaller particles. Okay? So temperature determines the crack propagation in these materials. This actually was the basis of Kyle Ramage's 2017 performance. Here you can see his graph. Actually, the graph was initially this, but he felt like the top panel was too complicated. But the point is this, is that if you cool from room temperature down to dry ice temperature, you homogenize the size of the fines. This should, in principle, then allow you to extract what he would describe as more evenly. But the terminal result of this is quite simply that you just have a bed of particles that is behaving more like perfect spheres. Okay? That means that we can start to predict outcomes. In his particular example, he noted that the coffee tasted sweeter, cleaner, all this stuff. That may be, but from a particle science perspective, this is what's actually happening. There's an added advantage of cooling the coffee is that the Eyring equation, which is an embodiment of the Arrhenius equation, states that approximately for every process, if you cool it down by 10 degrees Celsius, the rate of most of those processes will go a half. So if I cool something down from 20 Celsius down to minus 20 Celsius, that's half, 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 half. In other words, 16 times slower. So cooling down coffee actually decreases the rate of staling by 16 times. So the shelf life of 1 month becomes 16 months. You can imagine that a shelf life of 1 year for a green coffee becomes 16 years. So there's possibilities here of having verticals of coffee now, which is, I think that's awesome for a variety of reasons. You could quantify, for example, how your crop is changing with changing climate. You could quantify what was the best year. You could even sell vintages like George Howell does at Christmas. You get the idea, right? Okay, but you're going to do it. You got to keep it airtight because water loves coffee. It's been driven off in the roast, so it's going to now absorb water from the atmosphere. This is Michael Cameron, the guy who I'm about to tell you about all our work together. This is his freezer. And if you were going to freeze coffee, I'd encourage you to make it look something like this, food-safe bags. But there's greater implications than just being fancy and having all these geishas, there's the geishas stored, is that this is decaf. So individually dosed decaf is actually it has pretty big economic impact in the United States. Decaf stales at the same rate as normal coffee, but how many people in here are drinking decaf every day, right? Not many. So if you can individually dose and only use it when you need it, it saves a lot of money. So I've been working with a local cafe in Oregon, and over the last 2 years, they just small 2-shop place saved them $20,000. So small, but enough to pay for. So they pay for health insurance now for their staff. So that's cool. So let me tell you what I want to do. We did all that work because I want to develop, or I have developed a model for espresso, where I can numerically input things that matter, like particle size distribution, pressure drop, initial pressure P, radius of the basket, capital R, the radius of the particles, little r, the height of the bed Z, which is effectively determining the mass of coffee, in other words, the dose, and a variety of other things that we had to quantify experimentally. Let me give you an example of something you had to quantify. Temperature determines that K, that equilibrium constant K. I showed you Ka. The only thing that changes that is temperature, right? So as I go to high temperatures, the amount of caffeine, for example, is just easy to monitor, so that's what we did. The amount of caffeine that we were able to extract milligrams of caffeine per gram or per gram of dose, so per gram of coffee we use, at 90 degrees is about, let's say, 15 milligrams of caffeine per gram of dry mass. But if I brewed that same coffee at 20 degrees Celsius, I get only about 6 milligrams per gram of coffee. This is huge, right? Because it's saying if I use cold brew approaches, I cannot physically extract the same amount. We are limited by thermodynamics. So while people think that cold brew contains more caffeine, it's just more concentrated. In fact, you're being extremely inefficient doing this. You're leaving behind more than double the concentration of that material. But why I show you this is not the cold brew anecdote. In fact, it actually relates to the difference between caffeine and caffeic acid. Is that caffeic acid, for example, at all temperatures, I couldn't tell the difference. If I went up to 90 or if I did it at 20, I extracted all of it more or less. And that means then that the rate of extraction of caffeine is different to that of caffeic acid. So one would have to fit a rate for each compound in coffee. That is totally impossible. Okay, so we fit one rate for coffee. Okay, but in principle, we could fit more. And so this is what my model predicts. And what I should also mention, the reason we predicted only one rate is because we're measuring the extraction yield, which is on a device that measures an average mass, right? And hopefully you can see why the average mass extraction might be problematic if you see the parallel to that of the TDS probe, which is measuring an average ionic content. But in any case, one rate constant for extracting coffee stuff allows us to then predict the outcome of espresso shots. So for a real-life grind setting, on an EK43, on this particular EK43, you'd have to do something similar for yours. At a given pressure, in this case we did 5 bar, and a recipe of whatever this is, let's say 16 grams in, 40 grams out, you can then start to predict your extraction yields. So that's neat, because this is something really tangible that you actually do inside the cafe. On this side, we then control water pressure, and you can see that as pressure goes up, we end up with lower extractions. That's already pretty neat. Let's see what we can do here. First thing the model also tells us is that because we have one rate, the small particle made of the same stuff as the big particle is getting wet at the same rate. So this means that the fines are imparting most of the flavor into your coffee, and it's not the boulders. In fact, the boulders are a bit of a problem because they contain a lot of mass, but at a given time, they're not even wet. Right? So this is why the pre-infusion maybe helps. I know you can pontificate about this for a long time, but the point is you shouldn't hate the fines. They're the reason you even have an espresso, okay? So, what I'm about to show you is a series of experiments. This is my experimental setup, except for I had a different person standing there. But we were using the San Remo Opera version 1, and we were doing volumetric shots. So we needed 20 in, 40 out, but we quantified it. We know exactly how much coffee we put in, how much water we got out, just the same as what you would do. But I needed to do it a lot. So we pulled 3,000 shots, and I didn't do anything, actually. This is one of these things, when you get to the top, you do nothing. It's great. So, okay, so here you go. Here's the problem. So I'm sitting here and I'm grinding, right? And the expectation is that if I start at grind setting 2.3, that shot runs in, for example, 25 seconds, let's say. And I go to 2.1 and my extraction yield goes up because my surface area is going up, and I go to 1.9 and it goes up. And you can see the variability in shot time is fluctuating, but it's not a big deal. Then I keep going and I start to see a bit of variability in my extraction yield, and it goes up to at 1.7, surface area is still going up, and I know that my grinder is producing more and more and more fines. And I go to 1.5 and it goes down, and I go to 1.3 and it goes down, I go to 1.1 and it goes down. Now, coffee people would typically say this is channeling, right? This is water moving through the bed and not touching all of the coffee. And in fact, we're inevitably going to agree, but I want to show you more rigorously how to navigate this. The real problem is that people like it when it tastes like that. Over here. On average, you could be anywhere, but this is where, for this coffee, it tasted good. But the problem with this was the shot time was fluctuating anything between 30 and 40, and this is to 1 standard deviation. So these shots could be running in 25 seconds or 42 seconds at these given parameters, and somehow we decided this was the one we liked. Which doesn't make sense economically, right? Because if you're running a cafe and all of a sudden you pull a 20-second shot and it hits exactly this number, then you're like, I don't know what to do anymore, right? Do I throw it out? I don't know. So, the problem is that a 22% extraction it's complicated. It's the best we've got at the moment, and I was previously more negative than I am now. But the way the measurement works is you have a refractive index that you're going to measure. It's effectively a density, and the refractive index is like sort of like a percentage of the speed of light, the rate in which the light is traveling through the liquid. Now, the speed of light's constant, so there's some hard physics in that number, but the take-home message is that as you change the concentration of stuff solvated in water, you're going to change the refractive index of water, and therefore you're going to then somehow correlate that to the mass of coffee that was in that water. But that doesn't work so well because it turns out that ethyl acetate, for example, unorganic compound, and sodium chloride have different changes in refractive index for a given concentration. In fact, you could have 5% ethyl acetate in water, and it would read the same on the refractive index measurement as 1% of salt. Okay? This is a bit of a problem. Furthermore, refractive index is extremely temperature sensitive. So you can see the scale here is on the third decimal place, 0.5. Over here, it's also on the third decimal place, 0.5, and these are just minor fluctuations in temperature. Okay? Okay, but it's still the best we've got. So fitting a 1 rate constant to coffee matches well with a single measurement of extraction yield using a refractive index. Okay, so it's sort of a self-consistent argument, even though it's sort of fundamentally flawed. So here's the important point. My model is this blue line, and it matches experiment. I mean, that's pretty good. And then all of a sudden something bad happens, and we call this channeling. And so I'm inclined to agree with the barista, because channeling, indeed, if you taste a shot on this side, it tastes like over-extraction and under-extraction at the same time, but nothing good. Like somehow it's, I don't know, you get the idea. How could that even be? So I actually believe that that's true. So what actually is happening over here is if you are indeed channeling, then what you're going to be tasting is our expectation, which is provided by the model. So something like perhaps 24%. So some of the puck is going to be extracted to 24%. Some is going to be at 23%, all the way down to 0%. Some of the coffee may not have even seen water. Now that is, of course, an extreme, right? There's no way that that bed is going to be completely unwet in one corner of it somewhere. But you get the idea that as an illustrative example here, that this shot that tastes however it tastes right here is a combination of high extractions, much higher than you thought, as well as lower. So how do we navigate this? Well, it turns out that if all you care about is extraction yield, then one might just simply say, okay, well, can I get this 22% extraction simply by just finding a way to more evenly extract from it? And one might just do that by grinding a little bit coarser and then reducing the amount of water that you've used. So this is intuitive, right? This is what we do every day. We grind coarser and then pull the shot a little bit shorter. This would give us a more consistent shot. The shot would run much faster, and it would probably taste different, a different 22%. But nonetheless, 22%. So that's something you could, if you cared about that measurement, you could do this. Conversely, one might just use a little less coffee. Now, given that the model predicted that as we down dose, the extraction yields would go up, I could go from instead 20 in, 40 out to 15 in, 40 out. And now at a given grind setting, the extraction yields are rigidly bumped upwards. And so this is somewhat counterintuitive, but the only way one can access 22% using a 15-gram dose is by grinding much, 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 much coarser. So think about that. I'm saying to you, down dose to 15 grams and you want to get the same extraction, you got to grind it like, for example, maybe 2.5 on an EK instead of 1.3. That's day and night, but you're hitting 22%. But that shot's going to run in 7 seconds, but you're hitting 22%. So the smart person in the room might say, oh, I see what you've done here. You're going to go up here and then reduce the beverage volume. And then you're going to go down here and reduce the beverage mass. And so if I did this forever, I would have no volume and no mass. And so the best coffee, the most reproducible one would be one you didn't ever make. That is true. So this is problematic. So what we have to do in the cafe setting is we all decide, and I guess probably you don't think about it like this, but you all decide somehow either you have some size of your drink, that your minimum drink that you're acceptable to serve as an espresso, and perhaps for you in your cafe it might be 20 grams, maybe that would be really short, or maybe it's 60 grams, whatever. So that you determine this minimum, you determine the sort of optimized region up here, so then you just have to navigate down here. But some of you might be thinking more economically and say, I don't care about what volume this drink comes out at. I can only put 15 grams in that basket. Otherwise, I'm going to start wasting money here. So that's why the bottom half exists, is that now you're learning to navigate this region. But it doesn't stop here. Now things get a little more complicated. Okay, I told you before that based on the model, which seems to match reality pretty well, that we would expect to extract up here, something like 24% for that given grind setting. And you know, we've done this a lot of times, a lot of different coffees, different grinders, and you don't need to make this measurement to know that you're going over this volcano peak. You can do this by taste, right? So this is only here to help you see that this is actually a quantifiable entity. So I've done this a lot of times, and we go over here, and then we get to a shot that happens to taste good somewhere on this volcano, and we don't know where we are, but we know that as we grind finer, we should expect higher and higher extraction yields. So if this is our expectation, we think that indeed we are tasting some coffee that was extracted to 24%, or perhaps even more than 24%, but we're reading here, or we're tasting that over under. Why not then just traverse across like I told you before, and then you're going to end up with the same massive extraction, but it's going to taste pretty different because the shots run differently. Or alternatively, you should be able to see the volcano. Imagine the 15-gram volcanoes up here. I don't know why it's so faint in this picture, but the 15-gram volcanoes here. Alternatively, one might be able to traverse up and hit the expectation. Remember that 15 grams is going to be something like this, okay? So if I go up to my expected extraction yield, then I only need to grind marginally finer, so let's say 1.8 instead of 1.3, down dosing by a quarter, and then achieving these extremely high extraction yields. But by down dosing and by grinding coarser, these shots fly, like really fly. You know, sometimes in the cafe I work with in Eugene, we're now routinely doing 11-second shots, and actually just that alone, even though the coffee got better and more reproducible, 11 seconds in a busy morning is awesome, okay? So even just doing this is huge. But this is really neat because now I've shown you a way to achieve a really high extraction. Now, again, these may taste different, but at least now you're tasting what the upper component would be like. Perhaps you like that. Perhaps you wish that you had that upper and that lower. For example, you wish you had these two. So one might expect then that when this paper inevitably gets published, hopefully in a couple of weeks, that people will start to try doing this where you take one dose at 20 in, 40 out, another one at 15 in, 40 out, ground at 2 different grind settings, and if you mix them together, you approximate the flavor profile of this tasty point, but you have no shot variation in shot time or any of the extraction yields on the other side, the right-hand side of this volcano. This is totally crazy, right? But I think people can see what's happening here. So imagine stepping up, as we'll see in a moment, and the baristas will step up and have 2 group heads that are doing totally different things. That would be nuts. Okay, I know there's rules, but you get the idea. The point is that no one's ever going to do this, but it is a discussion, right? Is that I want people to understand that when you're on this side of the volcano and you're telling your baristas, they're like, it tastes over and under, and you're like, but I'm at 1.3. What should I do? And you grind coarser, and all of a sudden the extraction yields go up, and it's like you have no idea what's happening. It's just because of this. Now, let's see if I show you. Yeah, here. Sorry. So the way that I got my model to match the extractions on the left-hand side was all I did was reduce the mass of coffee in my puck. So in other words, we were channeling, right? That is what channeling is. It's just not accessing all that coffee. But there's an economic argument for not being on this side, even if it truly was that much better, like, you know, incrementally better than being somewhere over here. And it is that I can get to those flavors more or less. I can even get higher extractions, which means I'm being more efficient and less variable. For a minor decrease in the grind setting, and that's all I have to do. But the second thing is if I really did go up to this, I'm sorry you can't see that curve up here, but if I go up to this curve, I've reduced the mass of coffee I use by 5 grams. Now this is an extreme. I just picked 5 because it's a nice number, but in my experience in cafes that I've worked with in Eugene, they've dropped from 20 down to 17. And that 3-gram difference, as well as grinding coarser and running fast, has led to more reproducible shots, notably less to essentially no crema. So this is not really what people would typically think of when they see espresso, but it tastes like espresso and it feels like espresso, it just doesn't have the crema, for better or worse. And that's roast dependent as well. But by reducing the mass by 5 grams, you can do a back of the envelope calculation that if Starbucks and everybody were to do this, you save the United States $300 million a year. So it's a lot. And so actually perhaps surprising for you was that if you're going to down dose and you like that shot of espresso on the left-hand side of the volcano and you know that it's tasting over under, to dial that one in by down dosing, you're going to have to grind a tremendous amount coarser and ignore shot time. And this is in contrast to what the Specialty Coffee Association recommends for espresso at 25 to 35 seconds, mass of 25 to 35 grams, 92 to 95 degree water, all this stuff. This is directly arguing that that's not how this material behaves in that machine. Another implication that I didn't talk about is because this is a mathematical model, one can optimize the geometry of the basket, big R. Now, you needn't think about big R, as being the radius only of this. I could also optimize the shape of this. And so one of the conclusions that I have not shown, but will be sort of, I guess, a corollary to what we've talked about, is that perhaps maybe flatbed baskets are not the future for espresso, and perhaps maybe conical baskets are. The next thing hopefully I convinced you of is that fines are not the enemy. In fact, you should definitely embrace them. Without them, you don't have a shot of espresso. And that cooling coffee is some of the work that we talked about and has been used, and maybe competitors that we're about to enjoy watching might even be presenting cooled coffee, is actually giving you a benefit from a material science perspective. Now, whether that looks like and tastes like a different coffee or an improvement, that is entirely up to the barista to learn how to navigate that. And finally, one that I know you're going to be able to roll out in the cafe is that cold water limits the extraction of a variety of compounds in coffee, but non-linearly. So you're going to get totally different flavors by going hot or cold, using hot and cold water. And so as a result, actually, one might expect that cold brew coffee actually has way less caffeine, but might be more concentrated. And perhaps that's some of the reason why a lot of us don't really enjoy it, is because the flavor balance that we cupped with is, not only is it a different extract, it's like completely like you have no idea what the compounds are in that coffee anymore. So, I know that was a lot. I promised you the first half was going to be more heavy duty than this one. But if I could give you anything as a take-home message here, I was going to show you a picture of my mother, but I don't have one. So I have some collaborators. The reason I was going to show you my mom is she competed in the Cup Taster Championship. She's 65 years old and not in the coffee industry. And part of the reason I like working in this industry is I really am a chemistry professor. I get paid through National Science Foundation, these sorts of things. But it's an inclusive industry where you can actually work with a variety of people and learn things about something that actually matters. And so much so that, it was welcoming to my mother to even go in Melbourne and compete in the Cup Tasters. She got 5 out of 8 right in 1 minute and 11 seconds. She's a machine. Yeah, because she just doesn't care. Anyway, halfway through at the Cup Taste, she was next to Craig Simon, one of these Australian baristas, and halfway through she put the spoon down and looked at him and said, "You need to hurry up." So anyway, I appreciate the opportunity. Maria, thank you. Where are you? Somewhere. Oh, gone. Maria invited me, and really I love doing these events because you get an audience that likes to learn new things. So this has really been my pleasure. I'm really enjoying my time here in St. Thomas, and I look forward to talking to all of you. And finally, good luck to the baristas here. I've never stepped up on this side of it, but I've certainly been part of the teams. I know what it's like. It's a lot of work. So just try and relax, and we'll have a drink later on. Thanks very much. Does anyone have any questions? If not, I'll clear off the stage. Yeah. Yeah, so that's a great question. So in the so if I go back to, pardon me, I hate being the guy who does that. There we are. So here, yeah, you're right. So strength is a complicated one because on the top side, as I use the same mass of coffee but reduce the beverage volume, this is an increase in strength. As I reduce the dose, this is a decrease in strength. So these two are sort of working with each other. One thing that I didn't do the math because honestly it's just complicated is that I didn't work out, I mean we have that data, I just didn't present it, what the strength of a beverage extracted at 25 or 24% versus a beverage that's extracted on average at 22%. I have it, I should present that. But this is something one would have to navigate, right, to figure out what is the perceived strength. I certainly know they all fell within the region of what I would think of as espresso, somewhere between 8 and 11% as coffee solids. But that you're right. If you do just down dose and grind coarser, strength is going to drop. Yeah. Yeah, if you look at the first comment. Okay, this is a great question. The answer to this question is that a microwave is a frequency that deliberately targets a vibrational mode between two atoms in the water molecule. So if you were to microwave something that doesn't contain that much water, then only regions that have water in it get locally extremely hot and really hot. We're talking way higher than what you'd measure with your gun, right? It could be thousands of degrees, really, really hot. But then in other regions, it's not that hot. But on average, it's going to dissipate the heat through the bean, and so that's what James was showing, was it would be at 60 degrees or something and grind it. And then the results were, it seemed like he was not getting something bad, right? I guess that would be the take-home message from the video. I argued that actually heating the coffee would result in the reduction of the increase in size of the particles of those fines. But actually it turns out that at a critical point, which I was unable to quantify in my study, when you heat up to a certain point, the number of fines reduces tremendously. And the reason is that those cracks are propagating so slowly because they can't navigate anymore that you just get bigger pieces, much bigger pieces. And so you could find that you'd get these really clean cups because you wouldn't have fines when you're making a pour over coffee. And so that's really what he was seeing. But honestly, I mean, it was so hard. The reason I didn't quantify it was because heat dissipates really quickly in coffee. So it was really hard for me to make a stable measurement and say that coffee, when I ground it, was 61 degrees Celsius. When I did it in liquid nitrogen, I could do it right away. I was submerged in nitrogen and went boom, and into the grinder. It's, no time in that at all. But the heating, it was difficult. So I thought that there was two variables in that weren't controlled for appropriately, and that was what I verbalized. But in general, the point is that microwaving targets local water concentrations rather than the bulk material. And so, yeah, it's somewhat interesting, but I think his weird science posts are deliberately chosen to make you challenge what you think you know, rather than making something good. And he certainly did that. Yeah.
How does roast development fit into
Yeah. Yeah. So K, the value, the rate constant K that I had used to fit my blue line was for a given coffee, but K could be any value and in principle should be molecularly determined. So if, a K value for caffeine, a K value for chlorogenic acid, for all these things. And so if you change the populations, the initial concentrations of those, which is going to be determined by the roast time, the development time, temperatures, these sorts of things, then you're only changing your initial condition, but you're not going to change K. But the issue is I don't have a K for every compound. So there may be a tremendous difference in composition between a dark roast and a light roast coffee, or one that's been developed, or taken to 14 minutes versus 9. And if that's true, then there's a big problem. If you doubt my use of 1K, which I do, then you have a big problem with quantifying using this, because those are not, you have two different K values, then you can't, there are two different rates of extraction, then you can't make an average estimation of what you've extracted. There's a final comment on that, is that roast development, we thought we had sampled that when we published the paper. But actually, perhaps we didn't do it as rigorously as we could have, because you only have a finite number of resources, so we did 4 coffees. But we accidentally chose 4 coffees that were all exactly the same size as well. So we have 2 systematic errors there. One is the size of the beans were all the same, so we didn't see a difference in the fines and so forth. And then the roasts, we work in specialty coffee, so I didn't do the thing where I went and picked up the coffee that was roasted, taken to 16 minutes. And so I just didn't do it. So I'm sure that it looks different. But again, you don't need to make the measurement to do this, right? This is just drink your coffee and you'll know, right? You know when you're over here. This is over and under. And on this side, you're just like, wow, we could go higher. So with that, I encourage the judges to drink the coffee and make sure they assess it properly. And let's move on. Let's move on because I'm done talking for today.